Imagine you're decoding an alien language with only a list of sorted words. Can you reconstruct the whole alphabet? Alien Dictionary is a Pattern Mastery 100 Super Challenge. Regularly asked at Google, Meta, and Amazon to test your grasp of graph theory, topological sorting, and string manipulation. Over 40% of candidates either miss edge cases or get tangled in cycle detection. Master this, and you'll shine on advanced ordering problems. Let's break down Alien Dictionary using the basic method, giving you a foolproof plan for any graph-based string ordering challenge. Given a list of words sorted according to an unknown alphabet, return a string representing the alphabet's order. If no valid order exists, cycle, return. List of words, all lowercase letters, possibly with overlaps and missing letters, a string of characters, the alien alphabet order, or if invalid. Suppose you're designing a search tool for a new language, or analyzing a secret code with custom rules. An interviewer might ask, how would you deduce task dependencies from log order, or infer a dictionary structure from partial data? What's tricky? You need to infer order constraints between letters by comparing adjacent words. Must detect cycles. If two letters are required to come before each other, there's no valid order. Not all letters may be present in the input, and some may be missing from certain orderings. Build a graph. Each unique letter is a node. For every pair of adjacent words, find the first position where they differ. That's a precedence constraint. Edge, topological sort. Apply Kahn's algorithm, BFS, or DFS to produce a valid order. Use an indegree map to track how many incoming edges each node has. Add nodes with 0 in degree to the result. Decrease in degree as edges are used. Cycle detection. If at the end, you haven't used all letters, result is shorter than unique letters, there's a cycle. Let's clarify. If a word is a prefix of another but comes later, it's invalid. For example, ABC, AB. All letters in words must appear in the output. Edge cases. Empty word list. Return. Words with same prefix. Skip until the first difference. Cycle in constraints. Return. Initialize a graph, adjacency list, and in degree dictionary for all unique letters. Compare each pair of adjacent words. For each character, find the first mismatch. Add an edge from char 1 to char 2. Char 1 comes before char 2. If one word is a prefix of the other and is longer, return. Topological sort. Add all nodes with 0 in degree to a queue, while queue isn't empty. Pop from queue, append to result. Decrease in degree for neighbors. If in degree becomes 0, add to queue. If result length equals the number of unique letters, return as a string. Otherwise, return, cycle or invalid input. Let's implement solution 1. This comment tells us we're solving Alien Dictionary using a graph plus topological sort with BFS. This imports defaultIct for the adjacency list and DEC for fast BFS queue operations. This starts our solution class, the container for our function. We define alien order, which takes words sorted by an unknown alien alphabet. Our goal is to reconstruct that letter order. This initializes in degree for every character in all words. Each letter starts at 0 incoming edges so every character appears in the graph. This is O total characters. This creates the adjacency list. Each character stores the set of letters that must come after it. A set avoids duplicate edges. This compares each pair of consecutive words to extract ordering rules. We compute the shorter length so we only compare up to that point. This detects an invalid case. The longer word comes first but starts with the shorter word, like ABC before AB. That ordering is impossible. If this happens, we return an empty string immediately. We compare characters one by one, looking for the first difference. When we find differing letters, C1 must come before C2. If that rule isn't already added, we add the edge C1 C2 and increase in degree of C2. We break because only the first differing pair defines the order. This builds the BFS queue of all characters with no prerequisites, the possible first letters. We create a list to store the final alien letter order. Start BFS. We process characters with indegree 0 first. We pop a character. This letter goes next in the alphabet. We append it to the final ordering. We check all letters that depend on C. We reduce their in degree because one requirement is cleared. If a neighbor now has no prerequisites, we add it to the queue. This ensures we used all characters. If not, a cycle exists and we return an empty string. Otherwise, we join and return the alien alphabet order. And that's how the Alien Dictionary algorithm works. Build ordering rules, then use topological sorting to reconstruct the alphabet. Efficient, simple, and elegant. Let's test our function using this input. WRT, WRF, ET, RFTT. These words are sorted using an alien alphabet. not English. Our task is to recover the letter order that makes this list valid. Here's why the solution works. The algorithm compares each adjacent pair of words to extract ordering rules. Comparing WRT versus WRF, T versus F is the first difference. T comes before F. Comparing WRF versus W versus E differs immediately. W comes before E. Comparing versus ET, R versus T differs. R comes before T. Comparing ET versus RFTT, E versus R differs. E comes before R. From these rules we get. Chaining them gives the alien order, WERTF. And that's exactly what the program outputs. WERT. It satisfies all the inferred rules and matches the expected result. So, the implementation is correct. It reconstructs a valid alien alphabet efficiently and accurately. Now let's try solution 2. This comment tells us we're solving alien dictionary using DFS with topological sorting instead of BFS. This imports defaultIct, which lets us build an adjacency list where each key starts with a default set. This starts our solution class, just a container for alien order. This defines alien order, which takes words sorted by an unknown alien alphabet. Our goal is to recover that letter order. We create adjective, a graph where adjective C holds all characters that must come after C. Using a set avoids duplicates. This collects all unique characters from all words, ensuring every letter appears in the graph even with no edges. We loop over consecutive words to extract ordering rules. We compare only up to the length of the shorter word. This checks the invalid case, a longer word appearing before its exact prefix, like ABC before AB. In that scenario, we immediately return an empty string. No valid alphabet exists. We compare characters until we find the first difference. That first differing pair gives us the rule, C1 comes before C2. So we add the edge C1 C2. We break because only the first difference matters. We set up a state map to track DFS progress. 0 equals unvisited, 1 equals visiting, 2 equals done. This lets us detect cycles. We prepare order to store characters in post order. A flag to mark if a cycle is detected. We define the recursive DFS function. If the graph is already invalid, stop immediately. If we revisit a visiting node, that's a cycle. We mark the graph invalid. And return. If C is fully processed already, skip it. Return to avoid rework. Otherwise, mark C as visiting. We explore all characters that must follow C. We DFS into each neighbor. After exploring all neighbors, mark C as done. And append C to the post order list. We now run DFS on each character. If unvisited, start DFS. Perform DFS from C. If a cycle was detected, return empty string. Otherwise, reverse the post order list and return it as the alien alphabet. DFS records letters after processing dependencies, so reversing gives the correct topological order. And that's how the DFS-based alien dictionary works, building a directed graph from word comparisons, detecting cycles, and performing topological sorting to produce a valid letter order. Let's test our function using this simple input, Z, X. These words are sorted by an alien dictionary, and we want to recover the letter order. Here's why the solution works. Comparing Z and X, the first and only characters differ. Z must come before X, so the graph has one rule, ZX. DFS checks for cycles, finds none, and outputs the topological order. Reversing the post order gives a valid alien alphabet. And that's exactly what our program returns, ZX. It matches the expected answer, confirming the DFS plus topological sort logic is correct. So the implementation works as intended, clean, accurate, and reliable. Let's have a quick recap. We're given words sorted in an unknown alphabet, and our job is to reconstruct that alphabet's order. Conceptually, every unique letter is a node in a graph, and the order between letters is inferred by comparing pairs of adjacent words. Wherever the first mismatch occurs, that's a directional edge showing which letter comes before another. The main challenge lies in building the right relationships and detecting cycles. A valid order exists only if the graph has no cycles. We use topological sorting to determine that order, either through Kahn's algorithm, BFS, or DFS. Handling prefix conflicts and missing letters is key to getting it right. Here's the logical plan. Build a graph of all unique letters. Compare every pair of adjacent words to extract edges. Track indegrees for each letter. Run a topological sort, adding 0-in-degree nodes to a queue, removing them one by one, and reducing indegrees of their neighbors. If all letters are processed, we have a valid alphabet. If not, there's a cycle, and we return an empty string. We constructed the graph, established edges between characters, and executed Kahn's algorithm cleanly. The program ran successfully on LeetCode without any errors, producing valid alphabet orders for all non-cyclic cases. We verified the solution against various tests, valid dictionaries, invalid prefix cases, and cyclic dependencies, and every scenario behaved exactly as expected. All test cases passed. The key takeaway? Alien Dictionary teaches you how to think in dependencies, how local comparisons build global order. Once you master graph construction and cycle detection, problems that seem alien at first will start to feel like familiar territory.